You can find a 4 by 4 matrix whose square is minus the identity matrix. You can find another 4 by 4 matrix whose square is also the minus identity matrix. And you can find yet another 4 by 4 matrix that when you multiply the first two, you get the third. So there's enough flexibility in 4 by 4 real matrices to build a model of the quaternions. One way to build a model of things like this is to work with quotient spaces of polynomials. So do you guys know what z adjoint x is? So this is things like what? a0 plus a1x plus a2 x squared plus da 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 plus an x to the n, such that a0 through an are what? Elements of z, right. So this is the set of polynomials with integer coefficients. And let's see here. So let's see here. So the let me try to describe like this one. If we have things like a plus b times the square root of minus 5. How to say this? That's not quite it. I want to think about x equal to the square root of minus 5. If I think about x equal to the square root of minus 5, this is x squared is equal to minus 5, right? Or x squared plus 5 is equal to 0. So you can form what's called a quotient space. All right, here's the way it works. We can look at z of x divided by the ideal generated by x squared plus 5. And what this is it's things like this. It's things like f of x plus this x squared plus 5 thing, such that f of x is in zx. Now, this gets really old really fast, this kind of notation, right? So sometimes people would like to use something like f of x bar for the coset of f of x, all right? So the way this works is that basic property is f of x plus x squared plus 5, all right, is equal to g of x plus x squared plus 5 if and only if f of x minus g of x is an element of this x squared plus 5 thing. Now let me be more clear. X squared plus 5 with the parentheses around it, what that is equal to is x squared plus 5 times, let's say, h of x, where h of x is an integer polynomial. So two cosets are equal if their difference is just a multiple of x squared plus 5. I'm going to repeat that again. Two cosets here are equal, two elements. To repeat this again, f bar of x is equal to g of x bar only if f of x minus g of x is equal to like x squared plus 5 times some other polynomial h of x. Let's just build some simple lemmas, though. What can we say about x? Let's compare. For example, what's x squared minus 5? I'm sorry, x squared. Yes, I'll get with it eventually here, guys. X squared minus 5 is equal to what? can we write that as x squared plus 5 times some other polynomial? Two. You say 2x squared? Let's see, this is x squared plus 5 plus minus 10, right? Oh, I'm sorry. I've muddled something here somehow, guys. I'm sorry. Oh. I mean, the point here, and I gotta erase this because I've got some mental block on that at the moment. I'm sorry, guys. But this right here, the idea of it, just if I can be a little bit less formal for a second here, is that x squared plus 5 is basically equal to 0 in this quotient. So when you look at things like, you know, a naught plus a1 x plus a2 x squared, you know, plus da-da-da-da plus a n x to the n, well, this thing you can replace with minus 5, and so forth and so on. So you can like collapse it all down until you have something like a naught prime plus a1 prime x, right? So this plus the coset. Can be rewritten as this plus the coset. And so if you look at it, x times x is equal to what? Well, it's equal to x squared, but that's also equal to minus 5 mod this thing, mod this ideal x squared plus 5. So that means x is playing the same role as the square root of minus 5. This is a way of building z adjoin the square root of minus 5. I'm sorry, I have muddled the coset argument here a little bit. Finally, let me just end here with a little calculation due to Euler. And I want to show you how we can use these sort of factorizations to actually solve a real problem. So, yes, we have unique factorization in the Gaussian integers. We have unique factorization in z adjoining the square root of minus 2 as well. But at minus 3, something goes wrong. But at minus 2, it still works. So this, for example, if we had, if we're looking at y cubed equal to x squared plus 2, right? We can use z adjoin the square root of minus 2 to find the solutions. So the idea is simply this. See, this is x plus the square root of minus 2 times x plus the square root of minus 2. Minus. So sorry. But on the other hand, you've got y cubed. So if you have the cube of one integer, right? If you've got the cube of one integer, n cubed is equal to a times b, what can you say about the prime factorizations of a and b for integers? What structure do they have to have? n has a prime factorization, right? When you cube it, you get all the primes in its factorization cubed. That also has to match the product of the prime factorizations of a and b. So it stands to reason that a and b must be also the product of cubed powers of primes, right? So using prime factorization, the fact that if I have n cubed equal to ab, that forces a and b to also be cubes. Likewise, if I have y cubed is equal to x plus root minus 2, x minus root, what does that say? That says that x plus cube root of square root of minus 2 has to be equal to a plus b times the square root of minus 2 cubed. If there's a prime factorization in z adjoins square root of minus 2, this is a natural step to make. Euler made this step. Yeah.
Let's say n is a product of two primes that are both cubes. Couldn't you have two of one and one of the other?
Oh, yeah, you're right. But it's different here because they have the same, they have to share primes. You're right, my analogy isn't good enough yet. It's something more like this. So they're stuck with the same factors. I mean, that's very good. But then solve this. What's this give us? This gives us a plus b squared of minus 2 times a squared, right? Minus 2b squared plus what? 2ab squared of minus 2, yeah? And then multiplying that, we get a cubed minus 2ab squared minus 4ab squared. Is this what I'm supposed to do? Sorry, this feels wrong. Yeah. So what is this? Oh, man. Oh. So after you get, I do have it, okay. So that's a cubed minus, I was on the right track, I just have to stick with it, minus 6ab squared. And then the other term is what? 3a squared b minus 2b cubed square root of minus 2, right? I'm multiplying.
Yeah, but where did you get your factor from some cubes?
Just multiplying it out. Yeah. So that gives us two equations. The one is x is equal to a cubed minus 6ab squared. The other one is that what? 1 is equal to 2b cubed minus, 2b cubed minus, I'm sorry, it's minus 2b cubed plus 3a squared b. You can factor out a minus b there, right? Minus b times, or factor out a b, and that gives us 3a squared minus 2b squared, right? So what do you have to have? What does this tell you? This is this times that. What does this force b to be? Yeah, b is equal to plus or minus 1. And this has to be 0, right? Oh, I'm an idiot. That should also be what? Yeah, plus or minus 1, right? Duh. So we need the 3a squared minus 2 is equal to 1 as well. Or plus or minus. I mean, I'll stick with the 1 just for the sake of being specific here. And so that gives us 3a squared equals to 3. So a is equal to 1. So what does this tell us? This tells us that I've made a mistake. We should get x is plus or minus 5 and y is 3. Hehehe. All right, well, I'm sorry. We're out of time. I'll let Dr. Smith explain this mystery to you next time.